Hey everybody, welcome to Quicksilicon. In this video, we'd be taking a look at simulating the SKY130 SRAM macros, which are available on GitHub under the repository hosted by VLSI IDA. So it has like a bunch of different macros already generated for us, which contains all of the different information, which you would typically expect from a macro file. If you go inside here, you could see that it has the GDS file available, the LEF files, and as well as the VEROG modules are available too. So in this particular video, what I want to do is I want to take a look at the SKY130 SRAM 1 KB version, which has one read-write and one read port, and it has 256 rows, with each of the rows containing 32 bits of information. And the 8 here represents the write mask value, which the particular SRAM supports, which means that out of these 32 bits, you could have the mask applied at 8-bit granularity. So so what we want to do is take a closer look at the cell, the VEROG model of the cell, and what we want to do then is to write a CocoTB Test Bench, which goes and simulates the cell, and we're going to take a look at the waveforms in order to understand how the write is happening and how the read data is available out from the memory cell. So let's first take a look at the VEROG model of the SRAM cell itself. Alright, so I have the SKY130 SRAM macros repository checked out here. And as you can see, if I do an ls here, we get all of the different generated SRAM cells available to us. So let's go into the one which we would be simulating, that is SKY130 SRAM 1 KB with one read-write and one read port. And it is arranged in 32 bits of 256 sets, and the write mask is 8 bits. So if you go inside this, you would see like all of the different files are already present here. And what we're going to do now is we're going to open the VEROG model of the particular cell, and we would take a closer look at how this particular cell is implemented. We would then create a top level module which would instantiate this particular cell, and then a CocoTB test bench to basically read and write into the cell and look into the waveforms. Right, so the VEROG module, if you take a look at here closely, it has like certain power pins, and the module itself is called as the name of the cell, which is basically again 1 kilobyte, one read write, one read, and 32 cross 256 with 8-bit mask. As you can see that it has two ports, port 0 and port 1. Port 0 is just a read-write port, and port 1 only supports reading it out. What we're going to do in this simulation is we're going to only use the port 0 for now, and we're going to use it for both the read and the write cycles. And then it has like various different parameters defined depending on the number of mask bits, the data bits, and the address bit. As we know that it is 256 entries deep array, the address bit is basically 8 bits wide. So if you want to take a look at here as to how this particular cell could be imagined, is that we would have we could imagine this as the SRAM cell, and here the number of entries which it has is 256. That's why you have like an 8-bit address to basically address into each of these entries. And in a single entry, we have 32 bits of information stored. The other interesting thing which it also specifies is that out of these 32 chunk of information, each 8-bit can also be controlled, which means that it is divided into sets of 4, where this is controlled by write mask bit 0, this is controlled by write mask bit 1, similarly by bit 2 and bit 3. And if we take a look at the write mask width, it is actually a 4-bit signal, which means that they are actually utilizing 1 bit for every for each of these columns. So what could happen is that if, let's say, we only want to update this particular entry into the SRAM, we could then assert the mask bit for all of the others, but deassert it for this particular entry. The second thing to notice here is how the SRAM is architected. So if you take a closer look, the first thing which the SRAM does is that it registers all of the inputs. Here it says that all the inputs are registered, which means that when we will simulate it, we should actually see that the output data should not be available on the same cycle, because the all of the inputs are getting registered, which means that the actual read data would be performed in the next cycle, and that is the case for the write as well. So the write and read both will take a cycle to complete. If we go down further, this is done for both port A and port B, and yeah, so the actual memory cell is implemented here. As you can see that it has the data width here, which is 32, and the RAM depth, which is 256. So we could confirm that really quickly. So we can see that the RAM depth is calculated by left shifting the 1 by address data bit times, which is 8. So this would actually give us 256, and the data width is 32. Right. So the next thing is so looking into the mask operation, what we can see is that if the write mask bit 0 is asserted, then only the first 8-bit signal is captured, or 1 byte of data is captured. Similarly, if bit 1 is asserted, then we are capturing the next byte, and so on for the other 2 bytes, which means that the write mask signal needs to be 1, or basically 4-tick HF, if we want to basically write into all of the, or if you want to store the entire 32 bits of data into the SRAM. And then similarly, we have the control over each byte which gets written into the SRAM. This is particularly useful for using these macro cells in a RISC-V CPU, where the smallest or the granularity at which the data could be written in the data RAMs is actually 1 byte at a time, because we have instructions which just stores a byte or loads a byte out from the memory, and this is already handled as part of the SRAM here, which supports the write mask value, which can be used in order to get the actual byte of data to be read out. Now, the next section talks about the memory read operation, where it says that the write enable has to be 1 and the chip select has to be 0. So all of these signals are actually active low signals. So write enable being asserted to 1, since this is an active low signal, means that a read operation is being performed. Similarly, if the chip select is set to 0, it means that the SRAM is being currently enabled and the read operation should be formed. We could confirm that from the VEROG model here, where it does a NOT of the chip select registered signal and it with the write enable being 1, and then it gives out the data from the memory array itself. Similarly, the read for the next is also done on in the similar fashion. The write, as we noticed, it is being done when the chip select signal is 0 and the write enable signal is also 0, because both of these are active low signals. Cool. So now we understand like how the SRAM works in a very high level manner. Let's see if we could replicate all of this in the simulation world as well. Alright, so in order to simulate this SRAM, what we're going to do here is we have, let's say, the SRAM here. Let's call this as the SRAM model. And what we're going to do is we're going to create a top wrapper which basically instantiate this SRAM. So let's call this as the SRAM top. And this particular top model will have the pins which we define and will be connected to the SRAM wrapper. And finally, all of this would then be driven using the CocoTB Test Bench. So this is our CocoTB Test Bench. So this is how the test bench hierarchy and the RTL hierarchy would look like. The first thing which we want to do is we're going to take a look at designing the top level, and then we're going to go and design the CocoTB Test Bench to basically drive the inputs into the SRAM and then read them out similarly. So yeah, let's get right into it. Alright, so the first thing which we're going to do is we're going to create the top level, and let's call this as SKY130, yeah, the entire name, underscore top.v, and let's say that this is our SRAM top module. And what it'll do is that it'll just basically have the input and the output ports, and it will as well as instantiate the SRAM cell. So let's call it as SKY130. Yeah, let's copy this name and let's add underscore top to it. We'll see what input and output ports we need, and let's add it with the end module. All right. So the first thing is the clock, and the next thing would be the SRAM signals. The first thing would be the SRAM chip select, right? So the chip select underscore I. Similarly, we would have input wire SRAM write enable underscore I. So the reason why I want to do it this way is because I generally prefer active high signals over active low signals when writing the test benches. That's why I want to have like a wrapper which has all of the active low signals connected onto the SRAM cell. But when we are connecting them, you'll just invert that so that the active low signals which are used in the SRAM, they are correctly connected. The next thing which we want to see is the write mask, which is basically 3 down to 0, and that is called as SRAM write mask underscore I. And also the other thing to note is that we'll only be driving the port 0 of the SRAM. We will not have any signals defined for port 1 at all, and the clock for the port 1 would also be connected to 0 so that the clock doesn't toggle. The next thing is the address. So the address is another 7 down to 0. It's an 8-bit value. Let's call it as SRAM address underscore I. The next thing would be the incoming write data. So let's say SRAM write data underscore I. And finally, the output would be the read data from the SRAM. So let's call that as SRAM read data underscore O. Right. So we don't need to do anything here. So we just need to instantiate the SRAM. Right. So this would basically be the SRAM instance. And what it will look like is, let's copy the name again. And let's call this as SRAM. And let's hook up all of the different signals. So we have clock 0. So this would be connected to the incoming clock. Then we have CSB 0, which is basically the chip select, but this is an active low signal. So this would be not of SRAM underscore CS underscore I. The next thing is the write enable, which is write enable B0. And this would again be a not of SRAM write enable underscore I. And the next thing is the write mask, which is write mask 0. This would be connected to SRAM write mask underscore I, whatever the incoming write mask value is. Then we would have the SRAM address, which is called as address 0 in the memory cell. And this would be SRAM underscore address underscore I. Then we have the data input. This is the write data, which would be SRAM write data underscore I. And finally, we have the output data, and this would be the SRAM read data underscore O. We still need to connect the clock. So the clock 1 would be connected to 1 tick B0 because we don't want to toggle it. The next thing would be CSB1. So this can also be connected to 1 tick B1 because this is an active low signal and we want this to be disconnected. That's why we have connected it to 1 tick B1. The write enable, it's a read only port, and then we have the address 1. We could leave this disconnected, and as well as the output data, this could also be disconnected. Right, so this completes our top module. So this would help us write the test bench where we would be, the DUT would actually be this, the top module, and we would be toggling all of these different signals in order to get the data into the SRAM cell. So now let's try to take a look into the CocoTB test bench. All right, so we had the top module done. Now let's take a look at the CocoTB test bench. So I'm gonna open a new file here, and let's call this as the SRAM name underscore tb.py. And this would be our SRAM CocoTB test bench. All right, so the first thing which we want to do here is we're going to import the CocoTB Python library because that's what we're going to use for implementing our test bench. And the next thing which we want to do here is we would want to add the different triggers which we want to use. So the thing is we're going to use import CocoTB.triggers, and we're going to import the following triggers. We're going to import the rising edge. I think that's all what we're going to use for, at least for this level of test bench. We just want to wait for the rising edge trigger to be hit, and once that is hit, we would know that we have seen the rising edge of a particular signal, and in this case it will probably be the clock signal. The next thing which you want to import is the clock itself. So let's get the clock as call it as clock. So this would be import clock. Right, so now we have all of the useful information imported from the CocoTB libraries. Let's start with the CocoTB test. So the first thing which you want to write is a CocoTB coroutine basically. So that is called as CocoTB underscore coroutine. And let's call this as async def SRAM random SRAM test. All right, and this would take in the DUT. Right, so the first thing which you want to do here is to generate the clock. So this is basically our the stimulus generator inside of CocoTB, and what we want to do here is get the basically the clock generated here. So let's say generate the clock, and the way it's gonna be done is let's call this as clock is equal to we have clock dot it'll be CocoTB dot start underscore soon. We want to basically fork the process which starts the clock and let it run as a separate thread, and while this is being run, we would want to take basically drive different signals of the DUT itself. So that's why we've used the start underscore soon here, and what we want to start here is the clock, right, and it takes in different things. The first one is actually the time period. Let's call it as the first thing is actually the signal, so this would be DUT.clock, then the time period, and this needs to be specified in microseconds. Once we have done that, right, so the other thing which we also want to do here is that we do not want the first clock edge to be the rising edge. So what we can do here is we could add dot start and say that start underscore high is equal to false. So I think this needs to be like this. Right, so this would ensure that the first edge is actually a falling edge and not a rising edge. Now we could drive the initial values of the signals. The reason why we want to do that is because we do not have a reset here, so we would want certain signals to have like a proper reset value right when the first clock edge is seen. So let's do that, and the different signals which we want to drive here is DUT.SRAM chip select underscore I dot value. This needs to be driven to 0. Similarly, DUT.SRAM write enable underscore I dot value. This also needs to be driven to 0. So these are the two enable signals which, if are driven to 0, are good enough, and we will not see any excess getting propagated. And the chip select 0 is good enough, but yeah, the write enable also helps. Now let's wait for few cycles before we start driving our actual stimulus. How we can do that is by having a for loop in range of, let's say we wait for 4 cycles, and what we want to do here is we want to wait for the rising edge of DUT.clock. So we had already started the clock before, and the start soon basically forks away the clock into a different thread, and then we could do the await, where we are basically waiting for the rising edge, and we are doing that for 4 cycles. Now once we have done that, we are in a position to drive random stimulus to the SRAM. The way I want to drive the stimulus is what we're going to do first is we're going to write the entire SRAM. So we're going to write the entire SRAM here. We're going to start at random addresses, and we will keep on writing into them And as well as, like I mentioned before, the SRAM has the granularity to write into each byte within the column or for each row basically. What we're going to do is we're going to also randomize the write mask signal so that we are writing few bytes of the particular address which we are choosing. Now since we are writing random addresses, we're going to keep track of all of these random addresses too, because even though we run through the entire SRAM index here, which is basically 256 entries, since the address is random, there is a possibility that not all addresses are being written, which is why we're going to keep track of the addresses which are written, and then once we have done the entire write routine, we're going to read all of the data back which got written into the SRAM. So this way we will actually be seeing the SRAM behavior. And we will not have any checking implemented yet. That would be an exercise for you guys to go ahead and implement the checks using the CocoTB Test Bench. Right. So let's get on to it. The first thing which you want to do is drive random stimulus into the test bench, and we want to write that. So we want to keep track of the random addresses. So let's call this as SRAM rand address, and this would be a Python list. The next thing here is the for loop. So for I in range 256, because this is the depth of the SRAM, what we want to do is we want to first generate the random address. So the way we want to do that is using the random library. So let's import that as well. Import random, and yeah, so this can be done using and we would also want to append it into the list. So SRAM rand address dot append. What we want to append is the random address which we generated. So this would be random dot rand range. The minimum value is 0 and the maximum which it can go is 255. So the last would be 256, right? So this would generate a random number between 0 to 255, which will be our address for this particular cycle. And then we could enable the chip select. So this would be 0x1. We would enable the write enable signal as well. So write enable underscore I dot value is equal to 0x1. The write mask, like I said, that it would be random value. So this could be equal to random dot rand range 0 to 4, because the mask can take any value between 0, 1, 2 and 3. Actually it's a 4-bit signal, so it can take any value between 0 to 15. So this has to be 16. The other thing is the address, right? So SRAM address underscore I dot value, this would be chosen from the list itself, which would be SRAM rand address given by the current index. Yeah, so that should enable writing into the SRAM. And what we want to do now is to wait for the rising edge of the clock. So this is our entire write routine, and we will do the exact same thing for the read side as well. So this would ensure that we have written 256 times into the SRAM, and we will read, try to read all of the addresses which we wrote into the SRAM itself. So let's call this as read routine, and what we want to do here is again have the for loop and read it out randomly. So what we want to do is dut SRAM chip select dot I dot value is equal to 0x1, dut dot SRAM write enable underscore I dot value is equal to 0x0, and then we want to specify the address. Oh, by the way, one thing which we missed here is the write data. So let's add that as well. dut dot SRAM write data underscore I dot value, and this would again be a random data which gets written, and the maximum value is 0x1234 1234, right? So yeah, so this would ensure that we are writing random data into the SRAM, and then we want to read it out. The one thing which we are doing here is that we are reading out in the way we wrote, but I would ideally want to read out the random addresses from this particular list. So this can be done by shuffling the list itself. So let's do random.shuffle onto the SRAM rand address list. So this ensures that the contents of this particular list are now shuffled, and we would then be reading random entries out of the SRAM, not in the same way as those were written initially. Alright, so now in order to complete the read routine, what we want to do here is to add the waiting on the rising edge of the clock. So this would be duty.clock. Right, so this ensures that we are now reading out from the SRAM, and we are reading every time the random addresses which were written before. Finally, we are done here, but just before we do that, let's wait for a few cycles and then get this coroutine to be over with. So let's wait for a few cycles. Generally, I like to wait for a few particular cycles. But if you're doing that, let's keep the chip select to 0 so that we don't get any chunk data out from the SRAM. And the clock which we had forked out, it is good to handle it. So let's kill that particular process as well. Right. So this completes how our coroutine would look like. The next thing is the CocoTB test. So let's have this as the CocoTB.test. Yeah, so let's call this as def SRAM rand test, and it also gets the DOT. And what it does is basically it yields onto the coroutine, which was SRAM test, and passes the DOT onto it. Right, so this completes our CocoTB test bench for the SRAM. The next thing which is remaining is the make file in order to run this particular test. So let's create that too. Let's call this as make file. And the first thing which the CocoTB make file expects is the top level lang. So here it is VEROG. And the next thing is actually what is the name of your test bench, which is called as the module variable here. And the name of our test bench is the SRAM cell name _TB. So let's add that. So this would be TB. The next thing is the actual top level of the DUT. So this is called as the SRAM cell name with top. And finally, it needs the list of the files which it needs to compile, which is given in the variable called verilog sources. And the first one would be actually the SRAM cell itself. So let's call this as .v. And the next one is the top file. So that is _top.v. Right, so all of this is needed in order to get the simulation working. And finally, what we want to do is we would want to include the CocoTB test, the CocoTB make file. So this can be done by using the include keyword here, and we need to find where those make files is present. This can be done by running the command CocoTB config --make files. So this actually returns the path where the CocoTB make files are present, and from that path we want to pick the makefile.sim, because that actually sets up the entire simulation flow for the CocoTB. So once we have all of this, now we are in a position to run this on our end. Right, so let's go ahead and run this particular CocoTB test bench and take a look into the generated waveforms as well. Oh, in order to get the waveforms generated, we would need to add the VCD dump here. So let's add it here. Let's call the dump file as the name of our cell itself. So this would be this .vcd, and the dump vars would be anything which is present in top. So let's get that as well. Underscore top. Right. This would ensure that even the VCD file is dumped as we run the simulations. Cool. So let's try to run this on the terminal. What we could simply do here is we could just do make. Okay, so we're getting an error where it says that something, this particular file does not exist. So if you take a look at the yeah, so I think this is missing a dollar here because we wanted to treat it as a command. So let's do that again. And yes, looks like it's running, but it is saying that skipping simulation as only VEROG is supported on very later. Okay, so is it without the colon? Yeah, so looks like it went ahead, but now we are getting few errors from different things. So the first one, which looks like is invalid syntax. It is saying import CocoTB.triggers, import rising edge. Right, so this definitely looks incorrect. This should have been from. So let's do that. And let's try this again. Okay, so at least the errors have gone away. Now we are saying that SRAM right mask. Okay, so I missed underscore I here. And let's try this again. Finally, it should work now. Let's see. Great. Yeah, we do see that, it did passed, and we also have like some of the data being dumped out. So this is a part of the display statements added into the SRAM cell itself, but it's difficult to judge what is happening from here. So instead, let's take a look into the the VCD file itself. So I have the waveforms open for the SRAM which we've been trying to simulate, and what we can notice here is the hierarchy here. As we see that we have the cell name underscore top as the topmost hierarchy, and if we go down we have the instantiated SRAM cell, and then the different blocks of the SRAM which the cell itself contains. I have plotted the signals which we've been driving through our test bench, which were the ones which the top level uses. And if you notice that the initial few set, we are doing the write routine here, and you could see that the write mask is toggling as well as the read address. And we have the different, the write data being written. Actually, the address is missing from here. Let's add it. Yeah. So now, as you can see that we have different addresses being written as well, and the read data is throughout 0 because we haven't enabled reads yet. And let's take a look at how the read data behaves. So if we go ahead and zoom in, we see that the first time the read was performed was here, where we are trying to read the data which got written into the address 23. And if you notice here, the actual read data is available, after a cycle, and that too on the falling edge of the clock itself. And this is because, as we noticed, that the SRAM first registers all of the input signals, which means that this particular cycle, the input signals would have been registered and the actual read operation would have been performed here. But when the read operation does get performed here, it takes a few cycles for the SRAM data to be available, and that few cycles is represented here, where if let's take a look at the read operation being performed on the cell itself. So let's open the cell again, and if we scroll down onto the read operation, we see that it uses the negative edge of the clock in order to read the data out, and it also has like a delay associated with it. So if we try to take a look at what is the value of this delay, it is arbitrarily set to 3 right now. We could possibly make it to 0 or to some other value in order to get it right. And the other thing which you also notice here is that for few of the signals, you see that certain bytes have the correct value, while certain bytes have still unknown values, and that is because we were randomizing the right mask onto it. So the one thing which we notice here is that it takes a cycle to get the read data out, and then it also, the actual read data is only available on the falling edge of the cycle as far as these macros are concerned. So this is how you could actually take a particular SRAM macro from the SKY130 PDK and try to simulate it using CocoTB Test Bench. Hope you got a chance to learn something new.